And our next and last speaker is Dr. Claudia Wieners. So Claudia is a climate physicist at Utrecht University, and her main research interest is SAI and the effects of SAI on AMOC. And I think that's what she'll be talking about today. So please welcome Claudia Wieners.
Hey, I'd like to talk about basically what happens between SAI and tipping point in the North Atlantic, and in particular, what happens if we have waited for too long. Well, I mean, we now all know what the stratospheric aerosol injection. Pina Tubo has shown us the way, injected 20 megatons of SO2 in the stratosphere and cooled the Earth for 1 year. And if Pinatubo can do it, maybe we can do it as well. And Wake Smith, I don't think you showed that number today, but suggested it would be relatively cheap, like $20 billion per degree per year or such. Okay, so let's have a look. What would SAI do in the North Atlantic, to the Atlantic Meridional Overturning circulation and the North Atlantic Subpolar Gyre? So for those of you who are not that familiar with that system, so you may all know the AMOC or let's say the Gulf Stream system. It consists of a warm surface current carrying warm water towards the North Atlantic, where it gives a lot of heat to the atmosphere, giving us a relatively mild climate here in Europe. And then the water becomes dense enough to sink to around 1,000 meters and then return southward as a deep current. So the water that comes in is warm and salty, and because it's so warm, it can still float, and then it becomes cold and salty, it can sink down. And it is suspected, though there's a lot of heated discussion, that AMOC could be a tipping point. Here is a figure from a colleague of mine who did AMOC tipping simulations. So there's a concern that many climate models are like too stable for AMOC tipping, but they brute forced it a little bit and forced AMOC to tip in the CSM model. And that's the cooling effect in winter, which they found if they tip AMOC in a pre-industrial climate. So Norway would experience temperature drop of more than 30 degrees in February. To be clear, that's winter, and that's without the partial compensation from the global warming itself. So that's not exactly what we would get. But there would be severe climate change if AMOC were to tip. And even if it doesn't tip, it may still weaken, which also would be a problem. And why could it tip? Well, basically because this densification of the water that makes it sink could fail, either because less heat is given up to the atmosphere, or because the water becomes fresher from more precipitation, more river input, or more meltwater. Yeah, so I said already about the impacts. So let's talk also a little bit about the subpolar gyre. So the subpolar gyre is a counterclockwise current in the North Atlantic, and it is linked to AMOC to some extent. So as you may know, the sinking of water in AMOC doesn't just happen anywhere in the ocean. It happens in coastal current that have the coast to their right and densify while they go along. So that could be this currents around Greenland and Canada. And in the middle of these marginal seas, we have deep convection. So that's not the same as sinking, but that's water going up and down because of surface cooling. So you have cold water bubbles going down, and meanwhile warm water bubbles going up. But because of eddy exchange, having a cold interior of the ocean will also help to cool the coastal current and strengthen them and help the water to sink more. So there's an intricate link between the health of the subpolar gyre and AMOC, because the subpolar gyre with its convection region sort of helps the water in AMOC to sink down. And there's also suspicions that the subpolar gyre itself may be a tipping element. Scubin et al. Found that SPG subpolar gyre can tip in quite a lot. So let's say a strong minority of climate models. Okay, so now let's have a look at what SAI does to the system. So let's start with AMOC. We used a set of simulations based on the Glenn simulations to start with. So here's global mean surface temperature difference with respect to pre-industrial in an SSP 585 reference case without SAI, and in a case where we kept temperature constant at 1.5 degrees until a bit beyond 2100. So nothing special here. You see that we took quite extreme scenarios because we were not trying to mimic like policy-inspired scenarios, but we wanted to look at what could happen in principle. So we'd rather have a big forcing to see what can happen, and later research could maybe show whether it can happen in realistic scenarios. Okay, so that's the temperature response, and now let's have a look what it does to AMOC. So first we see here this red line, that's the AMOC response in RCP SSP 585. So AMOC weakens to something like 40% of the original value, so it doesn't tip here. But since models are likely somewhat too stable with AMOC, this could very well mean a substantial tipping risk because of this exaggerated stability. Now you see here a bit of a yellow shading. That's the SSP 126 ensemble from CMIP. You see that at least for the next 80 years, there's not incredibly much difference between the high emission and the low emission scenarios. So AMOC would still weaken. And then here the blue line, that's the RCP 585 with SAI. So AMOC still weakens a bit, but much, much less than in either of these scenarios without SAI, including the high mitigation scenario. So maybe even in a, let's say, much stronger mitigation scenario than our horror scenario here, some SAI may help with AMOC. I don't know. So here's a temperature response. You see that in the pure CO2 case, you still have a bit of a warming hole over the Atlantic. So that's the effect of the weakened AMOC and SPG. And you see with the SAI 2020, you see quite some overcooling in the North Atlantic because of this still remaining partial weakening of AMOC. Okay, so now our next scenario was like, suppose we follow this CO2 horror scenario, and in 2080 we think, oh shit, it's actually way too warm. So let's cool very drastically the Earth down. Again, this is meant to be an extreme case, not what we think will happen. But so it is possible to bring the global mean surface temperature down pretty quickly, well, assuming that some magic wand has produced the airplanes quickly enough. And this is what we then get for AMOC in the same scenario. So you see that in this green case, the late cooling, the further decline is stopped, but it's also not that the green line recovers to join the blue line. So at least for the next 50 years, and maybe much longer, we would be stuck with a much weaker AMOC than we would have achieved if we had done the SAI early. So we can recover GMST, but we cannot recover the ocean circulation. Here's the corresponding temperature pattern. So you see there's a massive overcooling in the North Atlantic because of this now stronger AMOC reduction. Okay, so to summarize the AMOC part, timely SAI can reduce AMOC weakening, depending a bit probably on the latitudes where you inject, you could maybe even fully compensate it. But delayed SAI is much less effective, and you even have a risk of sort of double cooling, because if you add to a cooling in the North Atlantic from AMOC, the cooling from the SAI, then you cool extra hard. Okay, so let's also have a look at the deep convection in the subpolar gyre. So here you see certain regions which are red here, and that's regions where we have a deep mixed layer, so where there's a lot of vertical motion in the ocean. So these are our deep convection regions. In the control scenario, so that's just a high emission scenario, all this deep convection vanishes, which could have bad impacts on AMOC. Now, if we do the early SAI case, we see that the Labrador deep convection region vanishes, but the other two are more or less preserved. So this one is weakened a bit, this one is actually slightly strengthened. But the delayed SAI does not give us back the convection at all. So if you zoom in a bit in the timeline of two of these regions, let's start with the Labrador Sea. We see that in the CO2 horror scenario, we just kill deep convection by something like 2050. And if we do the early SAI, even then we can't save the Labrador Sea, so it's maybe 10 years delayed, the problem. And we also see that here now sea ice comes in. But important for later, the sea ice only comes in after the deep convection is already more or less dead. Now, if you do the late SAI, well, deep convection has died long ago. It's not going to come back. And once we start the SAI, we get a huge increase of sea ice because the SAI cools. We can also look at this in another way. So here in the top plot, we have looked at the sea surface density, and we found that if sea surface density at the surface is high enough, which implies weak stratification, then we may not always, but at least we can get deep convection. But if the surface is insufficiently dense, then we will never get convection. And here we traced, so we have the color indicating density. This one is the critical density value here, this white line. And now we traced the sea surface temperature and sea surface salinity of our simulations. And we see in all cases at some stage we will get below this critical density line, so we can just not get our convection back. So it seems, so we were at first wondering a bit whether the sea ice is causing our loss of deep convection, but that's not the case because the sea ice always only comes in, at least in the Labrador Sea, after the convection is already dead. But it could help to stabilize the dead state because if there is sea ice, you get less temperature exchange with the atmosphere, and therefore it becomes harder to cool the ocean surface. So SAI may be to some extent counterproductive, not by killing the deep convection, but by making it harder, or adding one more mechanism to make it harder to get it back. Now we did the same stuff also for the Nordic region. So this should be 2080. By 2080, the deep convection is gone in the CO2 horror scenario. We preserve it or even strengthen it with the SAI 2020. And we see that there's very little sea ice in the region, despite the fact that SAI is cooling our climate. And in the SAI 2080 case, we see a temporary revival of convection, but at the end, convection dies. And once convection is dead, the sea ice increases massively. So SAI seals the region and makes it harder to ever recover our convection. So here's the same plot basically, but it's, well, same conclusions as with the Labrador Sea. Okay, so for the deep convection, basically deep convection can help AMOC in the long run. Early SAI can preserve it partially, namely in 2 out of 3 regions in the CSM. Late SAI does not preserve it. I should, however, add a caveat because these effects are pretty model dependent. So CSM is one of the most enthusiastic models when it comes to tipping the subpolar gyre. Many other models don't do it. So we should see these results as a possible scenario of what could happen and not as a perfect prediction. Just a small outlook. I may not need to convince you guys, but I still think we should take SAI seriously if you want to prevent climate tipping. Well, there are quite a lot of tipping points, as you all know, that can be tipped by as little as 2, maybe even 1.5 degree warming. And in a study also already briefly mentioned by Pete Irvine, we have looked at some of them and tried to estimate from literature review whether SAI would reduce tipping drivers for these tipping elements. So we came here up with a classification from overcompensation to no effect. And the amount of question marks is like how much evidence there is. And for many of these tipping points, we came to the conclusion probably SAI helps at least somewhat. We didn't find any where there's very convincing evidence that SAI would make it worse, but there are some for which there is basically just no research done. So we really should get a grip on what SAI or other geoengineering-like methods could do for climate tipping. It was mentioned in an earlier discussion session, the frustration maybe that the tipping community isn't really picking this up. I can confirm this because I suggested a session at the tipping conference next week in Exeter about SAI. It was turned down because maybe a journalist could come in and think that SAI is a great idea. That was basically the comment I got. However, I hope that this year's update on the tipping report will be a bit more balanced on SAI. I was pushing quite a lot there. So maybe at some stage they will turn around. And then finally, just because it's interesting, I tried to have a discussion with some of these SRM opponents, namely Jeroen Omen, who was on a non-use agreement, with Biermann et al. And we still disagree on a lot of things, but we actually found 5 points on which we agree. And even some SRM opponents now concede that a well-conducted SRM program could reduce physical risks. Of course, you could also make a bad SRM program with termination shock and mess things up even worse. And the biggest risks are, of course, the political ones like mitigation, deterrence, conflict, and so on and so forth. Okay, that's it from me. I welcome questions.
Questions for Claudia?
Thank you for a depressive but inspiring talk. If we take the consequence of what you say, if I hear you right, if we just let things go, we don't need CI's thickening because when the overturn stops up, the CIs will fix itself.
Well, I mean, that's the Atlantic sector, but it could be very different, for example, yeah, in the more Siberian sectors of the Arctic.
I have one on that side.
Hi, Adrian from the Australian National University. There's a lot of inertia and long timescales, anything in the ocean. And with AMOC tipping, my understanding is there's still a lot of work around early warning signals for potential bifurcation there. Supposing we had a decent early warning signal for AMOC or SPG convection collapse tipping, how long would that delay be between that signal and when, taking into account Wake's work, we could deploy? And where does that land in terms of, is it on time, or is it too late, or is it kind of in between? Because you had the 2020 and 2080 or 2070, but there's obviously a lot of time in between there. It seems it could be kind of a gray area.
So, first, I have my doubts about whether we ever will have a decent early warning signal, but even then, I mean, so you see in the plots for the Labrador Sea, so when would you say you have an early warning signal just from this time series? So maybe let's say 2030-ish. Well, already we have some declines here, but there's also a lot of fluctuation in the system. So now we have sort of used SAI before we even see an early warning signal, and the effect is this: we slightly delay the tipping. So even if you think that there's early warning signals that can give you 10 years or so, or maybe 20 for the deep convection, I doubt that that's like, yeah, I'm not sure if that would come and help us.
And then just a quick follow-up, the implication there would then be it'd have to be a precautionary principle basis for deployment, not that there's an indicator that tells you that, oh, we have to deploy if we want to avoid this.
Well, I mean, so if the only objective were to preserve AMOC, and there would be no political issues, then if in this ridiculous world, you would say, well, let's deploy this because otherwise the longer we wait, the more risk we take that we are too late. Of course, there are a lot of other considerations in the world, and that's why it's a dilemma.
Yeah, thanks. Great talk, Claudia. People don't talk so much about the actual added heat that's going to be in the southern part and the tropics when the AMOC shuts down. But we know from ice cores and things where it shut down in the past that it has and all of the extra heat from the greenhouse gases are going to be stuck around Africa and places in the global south. Do you want to comment about that?
Well, I'm not a paleo person at all. I do know that some people at our institutes, they did studies about the consequence of AMOC collapse, for example, for the Amazon rainforest. So there would be knock-on effects, let's say, way beyond the North Atlantic regions, which suggests that it's not a good idea to let AMOC collapse.
Yeah.
Oh, and sea level rise local, also not nice. So maybe we could flood Florida or something. I don't know.
So not all bad then.
Would polar SAI do a better job in keeping AMOC alive than global SAI? There was a nice paper by Bednarz, which I think is, at least there was a discussion paper on EGU, Bednarz et al. And from their paper, I would suggest that as long as you inject clearly on the northern hemisphere, that SAI is going to help you with AMOC, whereas stuff that you inject on the southern hemisphere is not particularly helpful, but you want a symmetric injection anyway for other reasons like the intertropical convergence zone. So just by judging from their plots, I guess as long as you also cool the northern hemisphere, it doesn't matter too much what you do. But this has not been super systematically checked, like comparing polar versus like non-polar directly under otherwise same conditions so far as I know.
So if I understand well, thermal density gradient is one of the drivers for keeping this thing going. Is that right?
I'm not quite sure if I understand what you mean.
The density from cold water is one of the drivers for this sinking.
Yes.
So I'm wondering if there, possibility of very strong local cooling strategies such as MCB to suck enough heat locally to drive this downward sinking, and if so, like, what's the energy flux that's needed to achieve this sort of locally driven sinking?
I don't have these numbers, and yeah, also it seems so I'm not. There's still discussion in the field about whether it's the temperature or whether it's the knock-on effects through precipitation and freshening that are the most relevant. So there's been a paper that suggests that in global warming so far, it was mostly the temperature change that has driven the AMOC or could drive AMOC weakening. If you ask Stefan Ransdorf, it's the salinity. So doing a local cooling, you would really carefully need to look at whether what it also does with the freshening. I don't think we can tell yet.
Back there? Maybe pass it.
Okay. This was not quite up to the stratosphere.
No. So I want to ask you about the climate that you imagine occurring when you had the post-collapse but very high levels of SAI. So the global average temperature is stabilized or reduced by SAI back towards pre-industrial, but you've got this there's no convection, so you've got this huge layer of sea ice. So one of the most underappreciated and important aspects of climate change is the temperature and the sort of clemency of the climate, particularly in the Oxford, Cambridge, London area. It's what people really care about. So if we have a situation where we have all that sea ice, could we face sort of dry, cold, tundra-like conditions? And if so, could it be directed at Oxford in any way?
Well, I mean, so if AMOC would collapse and you would do SAI, you could. So one thing is that you could still try to balance the very rough north-south temperature gradient by SAIing a bit more in the south, but locally around the North Atlantic, yes, it would be cooler and drier. I've looked very qualitatively into what would happen in Iceland. And so we have the sea ice, the fishermen couldn't go out, and the upwelling brings nutritious water there. That would also vanish if the Subpolar Gyre collapses, so that would definitely be dire. And I think in the rest of at least Northern Europe, it would be dire as well.
Oh, well, this is going to be the chuck of the century, this one. I've got to go right across the auditorium. Right, let's see how we go.
Not bad, Andrew. Thank you, Claudia, for a great talk. So this is related to Lars's point about interventions and mixed layer depth. We look at the chart on, we happen to have it on the left there, and the mixed layer depth. So how well do the models, you're talking about shutting down of convection, how well do the models actually represent what really happens when sea ice forms, and when, if you were to enhance that through the rejection of more brine, which then induces more convection, because that looks pretty flat in terms of the mixed layer depth. The mixed layer depth. So what's going on there, and how well do the models actually really work?
I don't think that the brine rejection will save you here, because I think much of the sea ice would come in from the north and still melt in the regions of interest in summer to some extent. But the brine rejection would happen even further north, but now the sea ice can penetrate more to the south with the currents. And this one is just, yeah, you will still get some mixing if there's wind in the summer, that kind of stuff. So that's why it's not totally zero, it's a windy area. But also I'm like, models are pretty biased with this. There's huge differences in where they have the deep convection and so on and so forth. So I would say that all these should be taken with a grain of salt, which would be good for AMOC with more salinity, but.
So yeah, kind of related to that, be interesting to hear your views on Danskard-Oeschger events and Heinrich events, because when we see these punctuations in the AMOC shutting down, they don't die, they come back to life very quickly with a vengeance. And so this death we have at the bottom here is flatlining. I mean, the historic parallels, they come roaring back in a matter of decades, but obviously here it's dead. So it'd be interesting to hear your views on, is that just a computer reason, or is there a physical reason why we don't see that historical analogy?
Well, I mean, it was a very different climate state back with Danskard-Oeschger, and I'm really not a paleo person, so I don't know very much about it. I know of a case where the simulated AMOC collapsed. I thought, oh, AMOC has collapsed, okay, and it was down for 1,000 years. And then someone took the simulation, ran another 500 years, and then it came back because this was a global warming simulation, and by then the deep ocean had also warmed, so that the density differential between the surface water and the deep water had to some extent been restored, because now the deep ocean had also realized that it was warm. So a long-term, very strong weakening of AMOC may not be a stable state, but a very persistent, like semi-stable state. But politically, I think what people care about is not whether it's a perfect stable state, but whether the AMOC is down for a few hundred years.
Or a few decades.
Sorry?
Or a few decades.
Yeah, well, at least a few decades, yeah.
Any other questions? Ah,
Thank you for this nice talk. I'm Martin from Tübingen. So as I see, also the SAI doesn't prevent the collapse, right? So there should be also, is there, how about the research in keeping these currents alive?
Well, okay, so SAI in this particular model, in this particular scenario, does not prevent the collapse of the deep convection in the Labrador Sea. It does prevent the deep convection in the collapse of deep convection in the Nordic Sea and in the Irminger Sea, and it strongly weakens the AMOC decline. So it doesn't do everything you may want from it, but it still significantly reduces risks in this particular model again. I'm not sure if that answers the question. Or was the question more about more stuff we should do?
Yeah, because
so one crazy suggestion that has been around was if you close the Bering Strait, so the other side of the Arctic, that reshuffles the salinity distribution. It could give us some respite against AMOC tipping, which may just about be the critical thing that just prevents us to go over the tipping point. Whether you want to close down Bering Strait with a big dam is, of course, a different question. I'm just meaning to say that there are things that you could in principle consider, but they're not in any way near a sort of risk assessment or such a thing.
I know this is, you didn't really address this issue in your talk, but if I can cheekily ask you, when you put together all of the recent work that's been done on AIM, what's your personal view about the likelihood of it significantly weakening in the coming decades, causing this massive freezing?
Well, whether it could tip as in reaching a near stable state that's off, I think that probability is still too high for comfort. And even if that's not what would happen, then a significant weakening that's not a tipping would already have dire enough consequences. Or just a tipping of the subpolar gyre without killing AMOC would also have dire. So if someone said if AMOC were an airplane, and the risk of tipping would be the risk of this airplane falling down, then nobody would ever enter this flight. So the risk is way too high.
Okay, let's thank Claudia once again.